Hello everyone, this video continuation to previous video, optical isomerism. So what are optical isomers? Optical isomers are the stereoisomers which can rotate plane of polarized light. So if optical isomer rotate plane of polarized light in clockwise direction, that is called dextroisomer. Or if compound rotate plane polarized light in anti-clockwise direction, that is called levoisomer. What is the criteria for optical activity? To show optical isomerism, to show optical activity, compounds must have chiral center. What is the criteria for optical activity? Criteria for optical activity is molecule with chiral center. Molecule with chiral center. Molecule with chiral center. What is chiral? What is chiral center? Chiral center may be chiral carbon. Chiral center may be chiral carbon or chiral axis or chiral plane or chiral helix. Anything may be chiral center. All these things are said to be chiral center. If molecule with chiral center show optical isomerism. What is chiral carbon? We know chiral carbon. What is chiral carbon? A carbon atom which is directly attached with four different atoms or groups, which is directly attached with four different atoms or groups. Said to be chiral carbon. Example this one, lactic acid, 2-hydroxy propanoic acid is lactic acid. In this one, first carbon, second carbon, third carbon, and second carbon is chiral. Second carbon chiral or not? Yes, chiral. Okay, so this is chiral carbon, so compound is optical active. Chiral carbon. What is optical rotation? Optical rotation is most priority group. First priority group oxygen, second priority group carbon with oxygen, carbon with hydrogen. Carbon with oxygen will become second priority, carbon with hydrogen third priority, and this is fourth priority. In which direction? 1, 2, 3 groups. 1, 2, 3 groups in clockwise direction. Fourth priority group on horizontal line. So anti-clockwise direction, yes, but fourth priority group horizontal line, S become R. This is R configuration. If you take this molecule, lactic acid only, your OH group pointing towards left, this molecule. For this molecule, first priority group, this one, second priority, third priority, 1, 2, 3 groups clockwise, and fourth priority group on horizontal line. Clockwise means R, but fourth priority group horizontal line means R become S. This is S configuration. Then how many optical isomers are possible? Optical isomers. Therefore, number of optical isomers is equal to number of optical isomers. Optical isomers means enantiomers. Number of optical isomers or enantiomers. Enantiomers is equal to. So only one chiral center is there. Terminals are different. Terminal groups are different. Number of optical isomers is equal to what? 2 power n. That is 2 power. What is n? N is the number of chiral centers. Number of chiral centers. N is the number of chiral centers. N is equal to here what? Only one chiral center. 1. 2 power n is equal to 2 power 1. That is equal to 2 enantiomers. 2 enantiomers possible for this one. These two are what? Enantiomers. These two are enantiomers. Dextro-levo isomers are enantiomers. Okay. So these two are enantiomers. What are enantiomers? Non-superimposable mirror images to each other. Non-superimposable mirror images to each other. COOH, it's mirror image, not superimposable. Mirror image means like this. This is mirror, COOH group. OH group pointing towards left, H right, and CH3. This is mirror image. Just mirror image. Whether it is superimposable or not, we have to verify. This is molecule. Its mirror image is this one. These two are mirror images. Which type of mirror image? Non-superimposable. To verify non-superimposability, rotation by 180 degrees. Top become bottom, bottom become top, left become right, right become left, left become right, right become left. If you place this one over here, non-superimposable because top CH3, top COOH. Non-superimposable. These two are non-superimposable. 1, 2, 3 are non-superimposable. 1, 3 non-superimposable means 1, 2 are enantiomers. 1, 3. 1 and 3 are non-superimposable. 1 and 3 are non-superimposable. 1 and 3 are non-superimposable. Therefore 1 and 2 are enantiomers. 1 and 2 are enantiomers. This is a different concept, non-superimposable mirror images concept. You have to verify like this. So change all position and place one. If these two are superimposable, that is not enantiomer. That become homomer. Superimposable mirror images are homomers. So take this one. Next, if two chiral centers are there, what happens? If two chiral center, molecule with two chiral carbons. In chiral centers, talking about chiral carbon. What are chiral center? Chiral carbons, chiral axis, chiral plane, chiral helix, all are chiral centers. Chiral center not only necessarily to be chiral carbon. Chiral center not only necessary to be a chiral carbon, it may be chiral plane, chiral axis, chiral helix. All are possible. So molecule with two chiral center. Molecules with two chiral center may be optical active or optical inactive. Molecules with two chiral center centers may be optical active, or inactive. Optical active or inactive. Molecule with two chiral center may be optical active or optical inactive. Example, take this one. OH here, and I will write a case. Molecules with two chiral center may be optical active and inactive. Case 1, if two ends are similar, if two ends are similar. Here, case 2, if two ends are not similar, if two ends are not similar, if two ends are similar, I am taking this example. Butane 2,3 diol, butane 2,3 diol. Okay, second molecule. Next I am comparing. Next, third one. If you compare these two, same molecule or not, or same molecule, butane 2,3 diols, all these are butane 2,3 diols. Yes, all these are butane. Compare these two also, and these two also. Okay. So first two are these two are diastereomers, non-superimposable, non-mirror images. Diastereomers. These two are diastereomers. These two are diastereomers. These two are diastereomers. These two are enantiomers. These two are homomers. See, how can I say? Assign this one. This is first priority, CHOH, CH3, CHOH, CH3, second priority, third priority. So 1, 2, 3 clockwise, 1, 2, 3, 1, 2, 3 clockwise, and if OH group on thick line, hydrogen must be on dotted line. Here hydrogen not given, that is the fourth priority group, only 3 bonds are there. 3 bonds are there mean fourth bond with hydrogen. Hydrogen position not given. If OH given on thick line, hydrogen must be on dotted line. Fourth priority group dotted line, clockwise direction R. Fourth priority group dotted line R. Okay. Next, if you see here, for this one first one, this is second one, and this is third one. 1, 2, 3 clockwise. Fourth priority group fourth priority group on dotted line. R configuration. R. Here fourth priority group, first priority, second priority, third priority. 1, 2, 3 clockwise. R. Here first priority group, second priority group, third priority group, clockwise. But fourth priority group hydrogen on thick line. OH dotted line mean hydrogen thick line. So if it is thick line, clockwise direction become S. Anti-clockwise become R. If a fourth priority group on thick line, then if fourth priority group present on thick line, then clockwise become S configuration. S configuration. See here. So first priority group, second priority group, third priority group, clockwise. Fourth priority group thick line means S. Next here, first priority group, second priority group, third priority group, clockwise. Fourth priority group thick line. Thick line mean clockwise become S. Clockwise become S. So here first priority, second priority, third priority. Which direction? Clockwise. Fourth priority group thick line. Clockwise become S. And here first priority, second priority, third priority. Fourth priority group dotted line clockwise become R. So see here, or otherwise I will write this one, especially this one. Okay, especially this one. If two ends are similar, RR and RR configuration and RS configuration, diastereomers. Next these two RS, SS. RS and SS also diastereomers. Next these two SS and SR. SS and SR. Then SR and RR. SR and RR. All those four are what? Or otherwise I will write like a table. RR, RS, SS, here SR. Okay, right. These two are what? Diastereomers. These two are diastereomers. These two are diastereomers. These two are diastereomers. And these two are enantiomers. These two are enantiomers. These two are homomers. What are homomers? Homomers are superimposable mirror images. Homomers are superimposable mirror images. Homomers are superimposable mirror images. Okay. If you take these two RS-RS configuration, these two are meso compounds. Homomers are superimposable mirror images. These mirror images are meso compounds for this one and this one. RS configuration. So like this. CH3, OH, H, OH, H, CH3, meso compound. Other is CH3, OH, H here, OH here, H here, OH here, H here, CH3. Meso compounds. What are meso compounds? The compounds which have internal plane of symmetry. So if you see from here, above, below, same. If you see here, on the green, above the green, below the green, same here, above, below, same. Meso compounds. These two are what? These two are meso compounds. Meso compounds. These two meso compounds are enantiomers. How? This configuration are 1, 2, 3. 1, 2, 3. Fourth priority group, horizontal line. Clockwise become S. Here 1, 2, 3. Anti-clockwise fourth priority group on horizontal line. Anti-clockwise means it become R. Here 1, 2, 3. Anti-clockwise. Fourth priority group horizontal line R. Here 1, 2, 3. Clockwise. Clockwise fourth priority group horizontal line. S. SR and RS. SR and RS are what? Meso compounds. These two meso compounds are what? Examples of homomer. These two are what? These two are homomers. Homomers. These two are what? Homomers. These two are homomers. Hope you understood. So this one meso compound, this one meso compound. These two meso compounds are homomers. Homomers. Superimposable mirror image. How to verify it? If you rotate it by 180 rotation, 180 degrees, then top become bottom, bottom become top. CH3 only, and left become right, right become left, left become right, right become left. If you place this one, they will become superimposable. 1 and 3 are what? Superimposable. 1 and 3 superimposable means 1, 2 are meso compounds. 1, 2 are homomers. Homomers are superimposable. Homomers are the isomers which are superimposable mirror images. Homomers are the isomers. Homomers are isomers which are, I will write like this. Homomers are isomers or isomers which are superimposable mirror images. Yes, these two are superimposable mirror images to each other. Superimposability verified by this method. Okay, take this one. Case 2. If both ends are not similar. If both ends are not similar. Both ends are not similar. Example, CH3, CHO, thick line, OH, thick line, OH. In previous case, CH3, both ends are same. Here both ends are not same. Next, CH3, CHO, OH, OH. Next one, CHO, CH3, dotted line, dotted line means below the plane, thick line means above the plane. Next one, CH3, CHO, here this is on dotted line and this is on thick line. Okay, how do you relate them? These two and these two. See, these two are diastereomers. These two are diastereomers. These two are diastereomers. These two are diastereomers. These two are enantiomers. And these two also enantiomers. Configurations, if you see fastly, configuration 1 2 3 1 2 3 dotted line, 1 2 3 clockwise R, here 1 followed by this is 2, 1 2 3 1 2 3, so 1 2 3, this become second priority. Anti-clockwise yes, RS configuration, RS here 1 2 3, clockwise R configuration, and 1 2 3, 1 2 3 means like this. Anti-clockwise it become R. Next here 1 2 3, thick line R become S, 1 2 3, thick line, this is S. Yes or no? 1 2 3, anti-clockwise but thick line R, here 1 2 3, clockwise but it become S, 1 2 3, anti-clockwise it become S. So RS, RR, SS, SR, all are diastereomers. RS with SR enantiomers, SS with RR also enantiomers. So remember this one. I will write like this. R gives RS, gives SR or SS, gives SR, all these are what? RR, RS, diastereomers, diastereomers, these two are enantiomers, these two are also enantiomers. Instead of homomers, enantiomers came here. Okay, take this one. Whenever different groups are present with two chiral center. So topic, optical isomerism, criteria for optical isomerism, chiral center may be chiral carbon or chiral axis. I will say chiral axis. Next, total number of optical isomers, how to count? If both ends are not similar, if both ends are same, we have different formula. If both ends are different, we have different formula. I have given formulas already. Okay, right, by using that one we can calculate number of stereoisomers. For example, this one, how do we calculate number of stereoisomers? Both ends are not similar, with even number of chiral center. Both ends are not 2 power n minus 1. 2 power n minus 1. 2 power n minus 1 means how many? Sorry, 2 power n. 2 power n means 2 power 2. 2 power number of stereoisomers, number of optical isomers, these are also called as enantiomers. Number of enantiomers are 4. Enantiomers, formula 2 power n, that is 2 power, number of chiral centers are 2, that is equal to 2 power 2 means 4. 2 power 2 means 4. What are they? RR, RS, SR, SS, total 4. Enantiomers are possible. Okay, take this one. Next one, allenes. Allenes means cumulative dienes. alkylidin, allenes, alkylidin, cycloalkanes, alkylidin, cycloalkanes, allenes, alkylidin, cycloalkanes, spiranes, and biphenyls. Biphenyls have no chiral carbon, but they are optical active. Due to presence of chiral axis. Example, first one, optical isomerism in allenes. In allenes, carbon-carbon vertical bond, and this is carbon-carbon horizontal bond. This bond is like this, this bond is like this. This is horizontal, and this is what? Vertical, this is horizontal. For horizontal bond, vertical. For vertical bond, horizontal substituents. This is like this. If these are R1, this is and R2, this is R3, and this is R4. R may be anything, any substituent. This is optical active. Where is chiral axis? This is chiral axis. Above the plane, below the plane are different or not? Yes, different. Okay, see this one. Carbon here R1, R2, this is R1 and this is R2. This is also optical active. Of course, two similar groups. 4 groups are not same, even though it is chiral. For chiral axis, 4 groups must be different. 4 groups may be different or may not be different, but 2 groups on 1 carbon must be different. R1, R2. Or if you see like this. If it is R1, this is R1, R2, decline R2, and this is dotted line, that is R3. Optical inactive, because these two are same or not? Yes, whenever plane is passing like this, R1. So this is not optical active because this axis is not chiral axis. This is chiral axis, this is chiral axis, this is not chiral axis. So green is what? Chiral axis. Here green is what? Chiral axis. This is what? Not chiral axis. To become chiral axis, above, below must be different, like this. So thus allenes show optical isomerism. Take this one. Next. Alkylidin cycloalkanes. Optical isomerism in alkylidin cycloalkanes. this is thick line, this is dotted line, R1, R2. So for this vertical bond, this is dotted, this one, R3, R4. Horizontal, vertical, horizontal, vertical, like this. So chiral axis is present or not? Yes, chiral axis is present. Chiral axis is present. This is chiral axis. Above, below plane are different. So above the line, below the line are different. So chiral axis. So this is the optical active. Similar to previous case, only difference is where double bonds, two double bond, here one double bond, one cycle. That is the difference. Remaining all are same. That means for this one also. Thick line, dotted line, R1, R2, thick line, R2, R1. Above, below are different. Chiral, optical active, like this. Next, take spiranes, optical isomerism in spiranes. Optical isomerism in spiranes. Like this. One is vertical, R1, R2, R3, R4, like this. This is what? Chiral axis. So this is what? Optical active compound. And in last one, optical isomerism in biphenyls. Optical isomerism in biphenyls. So take this one, I will write. Last one, optical isomerism in biphenyls. Note the number of, I forgot in last video, the number of rhythmic forms formula, number of optical isomers at the topic of number of optical isomers. Number of rhythmic forms is equal to A by 2. What is A? Number of optical isomers. Number of enantiomers by 2 or number of optical isomers by 2. This is the formula to calculate number of rhythmic forms. Remember this one. Write at the table where number of optical isomers calculated by formula. Optical isomerism in biphenyls. What are biphenyls? Two phenyl groups linked with a bond. This is one phenyl, this is another phenyl. These two are what? Phenyl groups. And this is what? Pivotal bond. I am taking rotation of single bond between two phenyl groups is restricted with proper substitution at ortho positions of phenyl groups. Rotation of single bond between two phenyl groups, rotation is not possible. Generally single bond rotation is possible, but here rotation not possible due to presence of we have to take one phenyl group, two phenyl groups I have taken here. So if is one group here, this is another group here, this is some X here and this is some Y here, both repel with each other. Then what happen? It become one is vertical and other is horizontal. One is vertical, other is horizontal. So this become chiral plane. So here R1 is present, bulk groups. So I am writing here R1, here R2, here R3, R4. R1, these two are repel with each other, It gives this type of structure. Decline here, vertical, R1, R2 here, R1 here, and R3 here, R4 here. Okay, this is chiral molecule. Chiral axis is present. Like this. So optically active. This phenomena is called as heteroisomerism. This is called important. This is called heteroisomerism. This is called heteroisomerism. Okay, take this one. In my next video I will explain previous bits on isomerism topic. With this isomerism completed.